Alright, so today I'm going to be explaining this important paper with the title Exploring Consistency in Graph Representations, from Graph Kernels to Graph Neural Networks. This NeurIPS paper in 2024. Graph neural networks have emerged as a dominant approach in graph representation learning, yet they often struggle to capture consistent similarity relationships among graphs. While graph kernel methods such as WL subtree and WL optimal assignment kernels are effective in capturing similarity relationships, they rely heavily on predefined kernels and lack sufficient nonlinearity for more complex data patterns. Our work aims to bridge the gap between neural network method and kernel approaches by enabling GNNs to consistently capture relational structures and in their learned representations. Given the analogy between the message passing process of GNNs and WL algorithms, we thoroughly compare and analyze the properties of WL subtree and WOA kernels. And we find that the similarities captured by WOA at different iterations are asymptotically consistent, ensuring that similar graphs remain similar in subsequent iterations, thereby leading to superior performance over the WL subtree kernel. This is the cosine similarity of 3 molecules from NCI1 dataset evaluated using graph representations for 3 consecutive GIN layers. Common GNN models fail to preserve relational structures across layers. So what we want is preserving this relational structure when we go from one layer to another layer. So the WL subtree kernel computes the kernel values by directly using the label histogram as a feature to compute the dot product. The WOA kernel applies a histogram intersection kernel to match substructures between different graphs. So this is the non-negative monotonically non-decreasing weight function. So given a colored graph, a feature map function, and a set of coloring functions, we define a set of iterative graph kernels that represents a composite function. Then the normalized kernel is given by this. The normalized iterative graph kernels are said to be monotonically decreasing if this holds. The normalized WL subtree kernel is neither monotonically decreasing nor does it preserve order consistency. So at each layer, pairwise distance matrix D is calculated using normalized representations of graphs in a batch. After randomly selecting a reference x sub k, the reference probability matrix is computed using distance matrix from previous layer, where entry n and m represents the known probability that graph x sub k is more similar to graph x sub n than to graph x sub m. So we have this consistency loss. So we use this cosine distance and the complement of cosine similarity in positive space is just 1 minus that. So this probability score is formulated using the sigmoid function. Given the distance matrix, the known probability that graph x sub k is more similar to graph x sub n than to graph x sub n. We can then minimize the discrepancy between the predicted and known probability distributions to enhance representation consistency across the layers. Here, we employ the cross-entropy laws to effectively measure the divergence between these two distributions. So the overall objective is both the consistency of pair distance relations for graph x sub k and the original loss. So they did experiments on proteins and other graph classification datasets. And they compared the GCN with the consistency, or graph isomorphism with consistency, and their method with the consistency.